So hello ladies and gentlemen. This week we are going to talk about the model performance, a matrix for regression and classification. We are going to talk about confusion matrix, and we'll learn about bias variance trade-off and overfitting and underfitting. So how can we define model error? So we have the training data represented by X. We have the target Y. So the model learns, right, by fitting a model to the training data with the help of the target Y. And then when we provide new data to this trained model, it will do predictions. And then we basically compare these predictions Y hat, right, with the target Y. And then we get the error. So this is the idea works both for regression and classification. The way it's calculated is a bit different. At the end, we want our predictions to be as close as possible to the target, whether it's continuous value or a discrete value. Okay. So regression algorithms, there are many different regression algorithms models out there. Linear regression, regularized linear regression, nonlinear regression, kernel regression, splines, and so on and so forth. So the general idea in regression is that you have the features represented by right x1, x2, and so on. And you want to fit a model, and in this case the model is defined by these parameters beta 0, beta 1, beta 2, and so on. And at the end, basically these beta 0, beta 1 values, these are this red line here. If you were to look at this figure, and that's your regression model. So in this case, it's a this is a simple linear regression graph, but there can be more complicated regression types as well. And on the left, you can see several different types that are out there. So R-squared is one of the most widely used model performance metric regarding regression. Right. So what does R-squared do? It can be defined as like the amount of variance being explained by the model. The variance within the dependent variable, okay, is explained by the independent variables. So you can also say it captures the value added from a model. And it basically is the value added compared to the baseline model. And baseline is defined as the average of your dependent variable, meaning the outcome variable, right? For example, if you were to do housing price prediction without taking into account any of the features of the houses, if you were to just take the prices of the houses, and if you were to average them, the prices of the houses within your training data, that will be your baseline prediction, right? That means basically, okay, I have no information whatsoever. I just have the prices given to me. So what should I do? I will just take the average, and that will constitute your baseline model. Now, when you start taking into account those features, things like the number of bedrooms, the size of the house, and so on, then basically what you want those things is that you want them to add some value. You want them to mean something, right? Otherwise, there's no point. You can just go with the average of the housing prices. When you start adding new information, you basically want your model to perform better. So now that comparison compared to the with the that new model basically that takes into account those features, you expect it to have a better performance. So that's R-squared, the performance of the new model compared to the baseline model. Okay, so you can understand it in that way as well. And the training R-squared can vary between 0 and 1. Again, be careful on this training part here, because basically what this means is basically train on the same data, and then you calculate the R-squared value on the training data. So it will be between 0 and 1. 1 means it's a perfect model now compared to the baseline model. It's able to explain all the variation within the dependent variable. A 0 would mean addition of those new features didn't mean anything. You know, they don't add any value at all. Now, when you go to the testing R-squared, you can calculate that as well. That can be negative too, okay? And the reason for that is if for some reason your testing data does not really, you know, look like your training data, basically if they're not coming from the same population, then your model that was trained on that was fit on the training data will not be a good model to predict on the testing data. Okay, so you can see negative values on that. It can also happen when you have overfitting, and we will talk about it more, because if your model is overfitting the training data, the R-squared will not be so good on the testing data. Right, let's continue. So how do we calculate this value? It's basically this base model value here, right? So this one. So this is the base model. You can see here that the mean is taken, and then the difference between each point and the mean is taken. It's squared and then added up. So this is your sum of square total, or sum of square means it's called as well. Okay, so this is basically this red line here. SS residual or SS fit, sum of squares fit, it's also called. Here you see you make a prediction based on your model, and then you compare to the actual value, yi, for each point in your data set. And then again, you take the difference and you square it, and then you add it up. That's the sum of squares, right? And then when you calculate R-squared, you basically say, okay, 1 minus SS residual divided by SS total. That will give your R-squared value. And you see there's the fitted model, sum of squared at the top, the base model, sum of squared at the bottom. So you say 1 minus because you really are caring about, okay, how much of a value did we add with these new features? Okay, and that can be seen here as well, because so you see, so this is the actual point. This is our prediction here, the blue line. So the total variance is basically when you just have the base model. This is the base model here. Base. So I'm trying to write with my mouse. This is the base model. So this is your error here. It's quite large. And when you have a new model, which is the blue line, right? That's taking into this X value into account. So the X feature, let's say that's the size of the house, for example. Now you expect the model to do better, so that's why you're predicting here, and indeed your error is much smaller. You see, it's much smaller. Okay, so this R-squared basically is, sum of all these points, the green differences divided by the red differences, the total of the red differences, the square of them, and then 1 minus, so that gives you the R-squared value. Okay, there are other metrics regarding regression as well that can be used, although R-squared is quite common. But there can be, you can see a mean absolute error, for example. Here again, the idea is very similar. The difference is, you take the absolute value. So this is the absolute value sign here. Mean squared error, it's again, the idea is very similar. You take the difference, you square them, you add them up, and divide by the number of points. Root mean squared error is taking the root of this. This is more relevant. Why? Because when you take the square, you basically are squaring the value of the interest, right? The same idea applies into variance and standard deviation as well. When you take the square root of standard variance, it becomes a standard deviation, which is more explainable, more understandable. So root mean squared error is basically taking the square root of this. Now the measure of this is the same as our dependent variable measure. Let's say, right, the dependent variable is in dollars, for example. If we go with our example, here the MSE is $squared. It's a weird value, basically. It doesn't mean much, but when you take the square root of it, it again becomes a dollar. So this is $squared, and this is dollars. All right, so root mean squared error together with R-squared is used quite a lot. Mean absolute percent error is very similar to this mean absolute error. You can see that as well, but I would say R-squared and the root mean squared error are the most common measures regarding regression. Okay, so let's continue. We have let's continue to classification algorithms now. We have the naive Bayes, for example, decision trees, random forest, logistic regression, support vector machines, neural networks, and then many more other classification algorithms. And the basic idea now is not fitting a line that best fits the points, but rather trying to separate these, for example, two groups of points, right? So that's the basic goal of classification. So then what's the metric that we can use to measure the performance of a classification model? Accuracy is one of them. It's basically comparing our prediction with the actual value. And here the predictions are discrete values, right? Or categorical values, basically. So, you know, for example, positive and negative, let's say there are two classes. So did we predict positive or negative in that case? The actual case is positive here, and the prediction is also positive, then basically this is the one means a indicator function that will just, what that means is basically, you know, if they are equal, the value is 1. Okay, when it's equal, the value is 1. When they are not equal, the value is 0. At least for accuracy, it's like that. Okay, so then basically when the points are equal, you're doing good. Your accuracy, it will add up to your accuracy. If you're doing a wrong prediction, then it will not count here. So at the end, you will have, let's say if you have 100 points in total and you predicted 90 of them correctly in this way of both classes, then your prediction accuracy will be 0.90, right? The 0-1 loss is the exact opposite of accuracy. It's the same idea. You just look at it from the other way. So it's, you can just call this the error value as well. Error in classification. So again, going back just here in regression, the difference, right? We are looking at continuous values. So the difference between them is basically some real continuous value, and then you try to, you know, close that gap as much as possible in your model. Here your predictions are class values, discrete values. Again, you want the values to be as close as possible. Here the definition of as close means basically you want the correct class to be predicted, right? So the idea is if it's equal, then you're doing good. If it's not equal, you're doing it wrong, or the model is doing it wrong. So here the actual value is yi, the prediction is yi hat. If it is not equal, then basically you're adding up it to the error value, right? If it is not equal, this value is 1. So this indicator function 1. If it is not equal, it's 1. If it is equal, this is 0. Again, here we are trying to calculate the error. So again, holding the same example, if we had 100 points and we had 10 points misclassified, then our error will be, or 0-1 loss will be 10 over 100. So 10 over 100. It's the reciprocal of accuracy. They should add up to 1 basically. At least for the binary case. Okay, so continuing on this idea, now we can, after we do basically classification, and we can calculate some of those metrics. The more relevant metric here is looking at the confusion matrix. What confusion matrix does, it's basically comparing our predictions with the actual class. Okay, that's why you have more detail here. So it's not only about correct or wrong classification or misclassification. It's like how did the model do the classification? Where did it do wrong? Okay, with this table we can understand more. On the left we have the actual true classes, and on the y-axis or on the columns here we have the predicted class. And basically if the class is 0, for example, a negative class, and our prediction is also 0, prediction is negative, then we have a true negative. Okay. If the class is 0, the actual class, and our prediction, the model is also predicting class 1, then we have a true positive. Okay, so these two are good things. We want these values as high as possible. Okay. Now, if the actual class was 1, but the prediction is 0, then we have a false negative. Why? Because we are falsely claiming, the model is falsely claiming that's the negative point, you know, it's a 0 point, but in actual, it is a class 1. So that's why it's called false negative. And if the actual class is 0, so it's in actual, it's a negative class, but the prediction is positive. So then what the model is doing, it's falsely claiming that that point is positive. Okay, that's why this is called false positive here. Okay. In some scenarios, you will see on the internet or papers out there that people show predicted class on the x-axis here or on the rows, and the actual class on the columns. So that can also happen. So that's why I try not to memorize these positions, but rather just understand the whole idea there. Okay, so the accuracy basically is the addition of these two, right? True negative and true positive divided by all these cells here, because that will give the total number of points, right? And the error will be the addition of these two crosses, the red crosses, because those are the negative, the misclassifications. And then divided by all the cells again. So here again, I tried to write this idea of entry ij. So if this is I here, so this is I. Okay, so this is I, and this is j here. Okay, so entry ij, so one of these cells in the confusion matrix shows the number of points in group I. So group I, in actual, it's in this here, in this value, in this row, but it's predicted to be in group J, meaning it's predicted to be one of these columns here. So a good model will have large values in green boxes and very small values in the red boxes. All right. Okay, so actually this will come next. So precision, recall, F1 score, and some other metrics. So based on this confusion matrix, there are there is some other metrics being calculated that's very relevant to assess the performance of a classification algorithm. And let's see what those are. So here again, the table, the confusion matrix. So accuracy, as I said, is calculated as the addition of the true classifications divided by all the cells. Error is 1 minus accuracy, exactly the opposite thing. Then we have the F1 score. The F1 score is again one of the very important metrics out there for classification. It's 2 times precision times recall divided by precision plus recall. So now what is precision and recall? So let's see that. So precision is true positive divided by true positive plus false positive. So that's here. So let's see what that is. So basically we are concerned with this column here for precision. Okay. What it does is it takes these true positive values and then divides by the true positive plus false positive values. What does it mean? It means the model is claiming some points to be positive, okay, and those positive points are true positive and false positives, okay? That's the outcome from the model. Now, some of these points are correctly classified and some of them are wrong. So the correctly classified positive points are called true positive. So here we're interested, out of those points that are claimed to be positive by the model, how many of them are correct? Or what's the percentage of this? You know, what's the ratio? So that's why we divide true positive by all the positive values. Positive number of points. Right? Okay. So recall and sensitivity, these are the same things. Recall is more used in the machine learning community. Sensitivity is more used in the statistics community or the medical community, but both mean the same thing. It's calculated as true positive divided by true positive plus false negative. So now that's, if you got the blue color here. So class 1 is positive, so you see we are concerned about this row now. Try to draw. Okay. So it's saying true positive. Okay, so this one divided by true positive plus false negative. So what is this row? It's the number of the actual class 1 or positive points, right? And then true positive means the points that were claimed to be positive and that are correct basically. So that's why it's true positive. But what this means is that out of all the positive points in the data set, how many of them were identified correctly by the algorithm? Okay, so that's why the true positive is at the top and all the positive points in the data set are at the bottom here. Again, that ratio. Okay, so these two are like very important. This one is also important. The idea is very similar. So instead of focusing on the positive points, we are focusing on the negative points. So you see it's dividing true negative, so this value here, by true negative plus false positive. So let me try to draw that as well. So that's, if you go with the green one for that, so that's this top row. Okay. Again, out of all the negative points in the data set, how many of them are correctly identified by this algorithm? Okay. So that's why true negative divided by all the negative points. Okay. So now we have learned about these metrics. So going back to this F1 score, it's basically taking this precision recall into account and then outputting a single value out of these two precision and recall values. So these two, okay, they go into this calculation and out we get a single value. Okay, good. So let's see here. So you might be wondering, okay, what's the importance of this? Why are we doing this? Why is accuracy not enough? Why do we need specificity, precision recall, and so on, or F1 score? The main point is if your data set is balanced, meaning it has equal or close to equal number of points from the different classes that you're trying to predict, then you're good. You actually don't even need these things. So accuracy would be doing a good job on assessing the performance of the algorithm. But in many cases, that won't be the situation. There will be more of one class. And so that imbalance can lead to unreliable conclusions if you were just to rely on accuracy. Okay. An extreme example would be, let's say you have 100 points, 99 of them are from one class, let's say true positive. So if you just let's say true negative, so it's all 99 from class 0, because that's, for example, in anomaly data sets, there will be very few situations where there is an alarm needed, or an anomaly basically happens only on a few occasions. So most of the data points will be negative, and only 1 or 2 situations will be positive. So in this case, let's say 100 points, 99 of them are negative, and only 1 is positive. If you were to just do an algorithm training, you actually don't need an algorithm. You can just, a simple algorithm would go like this. Okay, based on the data set, I will always predict negative. Okay, because 99 points are negative and 1 is positive. So what's the point in, trying to find a very good algorithm? You are already at 99% accuracy, right? If you were to classify everything as negative, you will get 99% accuracy. But then, that basically you don't have a model there. You're just, if anything, it's like a base model there, taking the majority class and just predicting everything to be of that class. So in order to prevent that kind of a situation, or basically to come up with a more reliable metric, these different the metrics are developed. Okay, for example, in that case, basically, let's look at so for example, the sensitivity of that model would be very low, right? Because you have 0 true positive. And because we are predicting everything to be negative class, so everything is on this column here. 99 of them are correct, 1 of them are wrong. Basically, okay, so 1 of them is wrong. And then this is 0, so we don't have any true positive. So our recall value will be 0 basically, or the sensitivity is 0. If you see a model like that, you can directly say that model is very bad, right? Because it's not able to predict the other class, it's just predicting a majority class. Now, if you didn't have this recall metric for this, right, we could not identify that. And of course, the precision is also I mean, it cannot be even calculated because it's like 0 divided by 0, right? Because we are not making any past predictions in our example, so we cannot even calculate it. So that basically signifies a bad model. So if you go to Wikipedia, you will find this nice big table with more metrics out there. I have only shown the most used ones. There is more out there, so if you're interested, you can definitely take a look at that. And you know, it's a nice table to know, so just showing it here. Okay, so let's do a few examples. For example, if you have this table, right? So we have true negative 50 points. We have, so this is actual, this is predicted, so false negative 5 points. So it was in actually a yes class, we predicted it to be no, so it's 5 false negative. Predicted is yes, so it's actually no, so that's why it's false positive 10 points. In actual it's yes, it's predicted to be yes, so 100 true positives. Okay, so here it shows the column and row totals. Okay, so in total we have 100, 150, 160, 165 points, and it's shown here. That's the total number of points. So overall accuracy is 165, goes to the denominator, and true negative and true positive is 100 plus 50, so that goes here. 150 divided by 165, it's 0.91. What's the misclassification rate? It's just the opposite of this one, or by opposite I mean just 1 minus this one, so it's 0.09. Or you can calculate it, it's the false positive plus false negative, 10 plus 5, 15 divided by 165. That's here. So true positive rate, okay, that's another name for sensitivity and recall. So let's first look at the table and try to find out ourselves, and then look at the calculation. Okay. So how many positive points are there in this data set? There is this many. So when I look at this row, 100 plus 5, there is 105 positive points. How many of them are correctly identified by the algorithm? 100 of them are correctly identified. So basically this ratio of sensitivity is 100 divided by 105. And that's what we have here. So it's 0.95. So this model seems to be doing quite good. So both the accuracy is high, that's good. Sensitivity is high currently, that's also good. So let's look at another thing we learned. So we learned precision, for example. Let's look at precision. So precision was checking, okay, the model made some positive predictions. How many of those positive predictions are actually positive? Okay, so where's the predicted? Yes, it's here. So we have 110 positive predictions. 100 of them are correct. So that means 100 divided by 110. So that's 0.91. So again, that's a very high number. That's good. So by just looking at these two numbers, sensitivity and precision, or recall and precision, I can say this is a good model. Okay. The accuracy is also high. So let's look at specificity as well, which is the out of the negative points, how many of them are correctly identified. So actual no, so there's 60 points and 50 of them are correctly identified. So 50 divided by 60 is 0.83. So again, that's a good number. So there's another metric shown here, false positive rate. So when you say false positive rate, you want that to be a low number, okay? So when it's actually no, how often does it predict yes? Right, that's false positive. False positive means basically it's actually no. It's a negative class, but the algorithm is predicting it to be positive. So when it's actually no, let's see where is actual no here. So this row. So it's 60 points, no points. And 10 of them are identified to be falsely, 10 of them are falsely claimed to be positive. So that's why 10 false positive. So false positive rate is 10 over 60, which is 0.17. So this is a good value. It's quite low. So we want these values, like false positive rate, for example, as close as possible to 0. And we want the values such as sensitivity or recall or specificity or precision to be as high as possible, and the largest value will be 1. And as far as I can see, the model is doing pretty good now. Misclassification rate, again, we want it to be as close as possible to 0. So again, it's quite low. Accuracy wanted to be high, of course, and it's high. So okay, another metric again shown here is false positive rate or prevalence. These are not too much used, but still it's good to know and calculate them if needed. So how often does the yes condition occur in our sample? So this basically just looks it doesn't look at the prediction, it just looks at in the actual data how many of the points are from the positive class. So there's 165 points in total, right? And the actual yes points are 105. So that's why the ratio is 105 divided by 165, and that ratio is 0.64. So this basically shows that, and that is the majority class, right? Most of the points are yes. So our model basically should do better than this. Okay, you can think of it that way, because 0.64 is like if I were to create a basic algorithm saying, okay, the majority class is yes, so every time predict yes, this is the accuracy I would get. So a model, any model basically, to claim that it's learning anything from the data should do better than this. And overall, the accuracy is better, for example, and the other metrics are also better. So I think the model is doing pretty good here. Another example, so let's say these are the values. So some of these metrics are calculated here. So I will leave this up to you. Please, by just looking at this table, calculate it yourself and then compare it with my solution here and see if you can get the same result. Final example, another table. And the results basically are shown. I did not show the calculations. Should be easy by now. Again, calculate it, compare it, and see if you can get the same results out. So for example, here, this previous model is doing pretty good. Accuracy is high, error is low, precision recall F1 are high. And when I look at this one, and I can see from these values, actually it's doing pretty bad, right? And you can see it here as well. So, I mean, the accuracy is high, but you see the precision recall, and that's why also F1 is not doing good. Okay, so next we will start with generalization.